You ever stare at a spreadsheet just packed with numbers and your eyes just glaze over? Raw data by itself can feel like a totally meaningless jumble. But here's the thing. Hidden inside all that data are stories, patterns, and truths just waiting to be found. And the key to unlocking them isn't more numbers, it's pictures. But how exactly do we turn that wall of data into a story that actually makes sense?
So that's our central question today. How do we take a chaotic list of figures and turn it into a clear, compelling story? Well, for the next few minutes, we're going to become data detectives, and our magnifying glass is going to be the humble graph.
You see, graphs are the tools we use to find those hidden stories. They let us see the shape, the trends, and the insights that are completely invisible when you're just looking at a list of numbers.
All right, so let's start with a quick tour of the most effective and, honest tools in our detective kit. These are the graphs that help us reveal the truth. First up, the dot plot. It's so simple, but it's incredibly powerful. Every single data point gets its own dot. Now, this is amazing because it means absolutely nothing is lost. You get the big picture, the overall shape and spread, but you can still see every single individual value. You can literally recreate the original list of numbers just by looking at this graph.
Look at this. See how quickly we can understand this data? With just one glance at these pulse rates, you can instantly see where they cluster, right around 60 to 70 beats per minute. You see the outliers, the full range. The entire story of the dataset is right there in one intuitive picture.
Next up is the stem plot, another really clever tool that shows the data's shape while keeping every single original value. It works by splitting each number into two parts. You've got the stem, think of it as the tens digit, and the leaf, which is the ones digit.
Okay, so here's how it works. Look at the very top line. The stem is 4, and the leaves are 0 and 2. This just tells us we have two data points, a pulse rate of 40 and another one of 42. When you see it all together, it's kind of like a bar chart that's been turned on its side, but it's one where every single original number is still perfectly visible. Pretty neat, right? But what if the story we're looking for isn't just about a single moment? What if it's about change over time? Well, for that, we need a time series graph. Its whole job is to reveal trends, cycles, and patterns by plotting data points one after another chronologically. So here we can track law enforcement fatalities year by year. And immediately we see the story, the peaks and the valleys, a really sharp spike around 2001, and maybe a downward trend in the later years. This is a narrative that only really comes to life when you plot the data against time.
Now, let's talk about categories of data. We all know the basic bar graph, right? But a Pareto chart takes it a step further. It's a bar graph with one simple but really powerful rule. The bars are always arranged from tallest to shortest. This one simple trick immediately draws your eye to the most significant categories.
Check out this chart showing the causes of fatal plane crashes. Because it's a Pareto chart, your eye is immediately drawn to the tallest bar, pilot error. The sorting basically forces you to focus on the most frequent cause first. This is the Pareto principle, the 80-20 rule in action, showing how a few key causes often drive most of the outcomes.
And of course, we have to talk about the pie chart. It's probably the most famous graph of all. Its job is simple, to show you how a single whole is divided into parts, with each slice representing its share of the total.
Here's that same plane crash data, but now it's in a pie chart. The focus shifts a little bit. Instead of just seeing which cause is the biggest, we now get a much better sense of what percentage of the total each cause represents. We can clearly see that pilot error makes up a huge slice of the entire pie.
Okay, our last stop on this tour is the frequency polygon. Think of it like a histogram, a bar chart for data ranges. But instead of using bars, it uses a connected line. This makes it really easy to see the overall shape of the data's distribution, and it's especially useful if you want to compare multiple datasets on one graph.
So here, the frequency polygon shows us the shape of commute times. We can easily spot the peak. The most common commute time is around 22 minutes, and then we can watch how the frequency of longer commutes just kind of drops off.
So we've seen how graphs can reveal the truth. But now for the twist. The exact same tools can be used to distort that truth. And one of the most common, most deceptive tricks out there is starting the vertical axis at a number that isn't 0. Just look at these two graphs. They are showing the exact same data. The graph on the left, which starts its axis at 10%, makes the bar for OxyContin look massively taller than the placebo. It totally exaggerates the difference. Now the graph on the right, which honestly starts at 0, shows the true, much smaller proportional difference. The takeaway here is simple, but it's absolutely crucial. Always, always check the y-axis.
Another major offender is the pictograph. These use drawings of objects to represent numbers. And while they might look fun and engaging, they are very often designed to mislead your brain by playing tricks with geometry.
So take a look at this example. The number of records in year 2 is about 3.5 times the number in year 1. But does that second telephone look just 3.5 times bigger? No way! It looks huge. Our eyes don't just register the height, we register the total area. And that's where the distortion happens.
And here's the simple math behind the deception. If you have a one-dimensional number, like a budget, but you represent it with a two-dimensional shape, well, doubling the budget doesn't just double the shape's height. It doubles the width, too, and that increases the area and the visual impact by a factor of 4. And if you use a 3D object like a cube, it's a factor of 8. This is Visual Deception 101. It's an easy, powerful way to make a small change look enormous.
So how do we protect ourselves from this? And how do we make sure our own graphs are honest? We need a code of conduct, a set of principles for visual integrity.
The legendary statistician Edward Tufte is a pioneer in this field, and his guiding philosophy is captured perfectly in this quote. A graph's job is to serve the data, not to be some piece of decorative art that distracts from, or even worse, distorts the data.
So here are his core principles for creating honest graphs. First, for really small datasets, just use a table. It's clearer. Second, make the data the hero, not distracting design elements. Third, your goal is to reveal the data's true nature, not twist it. And finally, almost every single drop of ink on the page should be used for the data itself. No fluff.
So I'll leave you with this question. From now on, when you see a chart in the news or in a report or on social media, you have the tools to be a data detective. You can ask the right questions and decide for yourself. Is this graph showing me the truth, or is it trying to hide it?